Great, so you can see my slides?
All right, I think we're good to go.
We're good to go, you can see my slides?
Oh, just Greg recently got his PhD and is now a postdoctoral researcher at Monash University under Kevin Modi. His work is primarily focused on developing process tensor tomography, a framework for fully characterizing non-Markovian processes on quantum devices. More generally, his research interests include quantum information, quantum characterization, stochastic processes, and the structure of correlation in both time and space. Let us all welcome our speaker.
Great. So thank you, everybody, for having me to give this talk. So today I want to talk a little bit about this recent paper of ours, filtering crosstalk from Bath non-Markovianity via spacetime classical shadows. So just as a little bit of a primer for what to expect here, I want to give a bit of a background of what quantum non-Markovian processes look like, and in particular, how these can be sort of like dynamically equivalent to temporal correlations, which are generated by crosstalk. So we have a lot of work in terms of, so these three references here look at characterizing temporal correlations on open quantum systems in practice. So given some quantum device, how can you learn its non-Markovian dynamics? So I won't go through those in detail, but I'll give a little bit of a brief background about that, and then talk a little bit about, to go through this recent paper, which is how you actually filter out the effects of nearby qubits in order to completely see what the bath is doing to your system. So I will just say, feel free to interrupt with any questions or anything that you have. I'm more than happy to kind of have this be more discourse rather than a monologue, but yeah, let me know. So to give like a brief kind of setup of the problem, what we're interested in is stochastic dynamics in quantum systems, because with any real quantum system, you're invariably going to get some kind of an inextricable coupling between the system and its environment. And as soon as you trace over environmental degrees of freedom, then your nice deterministic Schrodinger evolution becomes a probabilistic mixture at the system level. So you end up with stochastic evolution rather than deterministic evolution. And this sorts of effects give rise to familiar kind of stochastic noise issues in quantum devices like relaxation and dephasing, which are relatively straightforward to deal with or to understand, but also more exotic effects like non-Markovian memory effects. So maybe as like a simple understanding of these two regimes, if you have a weak coupling to maybe a relatively large dissipative environment, then you essentially get the loss of information, the dissipation of information in one direction. And this is easy to describe from a dynamical viewpoint because you only need to describe how the system evolves as a function of time and then what information is leaking out to the environment. So it's not ideal, but it's easy to get a handle on. At the other end of the spectrum, if you have potentially a stronger coupling to a smaller or more coherent environment, then you can get more like a mutual exchange of information. And this is problematic because if you apply a gate to the system, so you manipulate it in some way, that can determine what information travels out to the environment. The environment will sit on that and digest it for a few moments, and it'll send information back in, which depends on the gate that you applied at the earlier time. And so this generates a temporal correlation between what you did to the system as the experimenter and future dynamics. And so these sorts of correlations are much, this sort of noise is much more difficult to understand and to characterize. So in the context of quantum computing, what you can imagine is you're maybe running a circuit on many different qubits, and every time you apply a gate to the system, this is essentially an event. And if the qubits are coupled either to each other or to some common bath, then each event has kind of causal consequences. So information can be exchanged between neighboring systems or between systems and the environment. And that can come back to generate temporally correlated errors, or more generally, spatiotemporally correlated errors, where some choice of operation in the past on this qubit might affect some future outcome on a different qubit at a different time. So these kind of correlated errors are problematic in the sense that they can be hard to understand or to characterize. So you have exponentially greater number of outcomes in your joint probability distribution. They're also problematic in the context of quantum computing, because if you have correlated errors, then you necessarily have more error in your circuit. And finally, they're extremely problematic because correlated errors can either reduce or eliminate the effectiveness of quantum error correction. So they can effectively reduce the effective distance of your error correcting code. So quantum devices which have non-Markovian noise are much more difficult to kind of tame than their Markovian counterparts. And as we're kind of understanding in recent years, pretty much every quantum system which is available to us is non-Markovian in some way or another. So this motivates us to try and characterize, to get a handle of, and to mitigate these sorts of effects. So the kind of classical Markov condition, which you might be familiar with, is this statement that the probability distribution describing the future state of your system, so the state of your system at some future time, doesn't depend on the whole history of that system, but it only depends on the state of the system at the previous time. And you might wonder whether this generalizes to the quantum case, whether you can kind of come up with an equivalent condition. And one way to think about doing this is with the conventional open systems picture, which tracks the state of the system as a function of time. And you might wonder whether you can say, is the state of my system as a function of time, does it depend on the state at different times, or does it only depend on the state at the previous time? But there's a sort of a flaw in the thinking in this sense, because this classical condition comes with the implicit assumption that you can measure the system without affecting its future evolution. So, classically, if you roll some dice, then seeing the outcome of those dice isn't going to actually influence the dynamics. But quantum mechanically, if you make a Z measurement versus an X measurement versus no measurement at all, then these are going to affect the future evolution of the system in very different ways, because you collapse your wave function. And so this picture of tracking the state of the system as a function of time is insufficient for describing non-Markovian processes in general, because correlations at different points can't be measured without disturbing it. That, you can only infer things like if you see that your system decoheres and then recoheres, you can witness non-Markovianity, but these are sufficient and not necessary conditions for it. So an alternative approach to characterizing or to thinking about open quantum systems pictures is to do away with the idea of a state altogether, because as an experimenter in the lab, you don't actually have access to quantum states. What you have access to is a series of control knobs which manipulate that state. And so what you might imagine is, instead of tracking the system as a function of time, you track its response to different control operations. So imagine your system is evolving and you apply a gate of some sort at time t1 and you apply a gate also at time t2. Different gates that you apply are going to send this system on different trajectories in a way which depends both on the operation and the dynamics which the qubit or the system more generally is subject to. And the basic idea is that if you measure the response of your system to different control operations, then because quantum mechanics is nice and linear, you can take linear combinations of these control operations and learn something or infer something about the different trajectories between these things. So kind of the more general idea here is that if you want to determine whether you have temporal correlations, then you need to do enough operations on the system at different times in order to be able to infer all of the multi-time statistics. And I'll unpack that statement a little bit more on the next slide. But the general picture that we're dealing with here is what's depicted down here, which is that you have a system and it's subject to some uncontrollable system environment dynamics. So you have different unitaries, different unitary operations, different unitary interactions between the system and the environment, which could be arbitrarily strong. And simultaneously, the experimenter is driving the system with operations, this A0, A1, up to AK. And you can determine what the state of the system is conditioned on these an object known as a process tensor. So the kind of opaque definition of a process tensor is that it's a multilinear mapping taking in sequences of operations at different times and outputting a final state which is conditioned on those control operations. But really, you might imagine that it represents everything about the uncontrollable system environment dynamic. So it takes in these controllable operations and, depending on the uncontrollable dynamics, outputs the final state at the final time. In particular, because nothing is averaged over, we're not looking at averages over the environment, or sorry, we're not looking at averages over different steps. Then this is valid for arbitrary non-Markovian processes. So this multilinear mapping is valid for any open dynamics. And I just want to unpack this a little bit further, what that actually means. So this this depiction that we're considering, which is a driven quantum system over many times, you can imagine that at each given time, the state of the system is coming out. It's being fed into whatever your control operation is, this A0, which manipulates the system and then sends it back in to participate in the dynamics. And then this is repeated again and again. Now, imagine that you zoomed in just on a single one of these steps. Then this is exactly described by a quantum channel, so a dynamical map taking you from one time to the next. You can feed a state in to this channel and then get a state out at the next time, which depends both on the state that came in and on whatever these reduced dynamics are. But if you zoom out to multiple times, then what you might find is that your choice of A0 at the first time, by virtue of this system environment unitary, unlocks some degree of freedom in the environment or changes something about the environment, and then comes back at the later time. So then at the next time, when you feed a state in at this A1, the state that you get out depends not only on the state that was fed in, but it also depends on your choice of control operation at A0. So this is a quintessentially non-Markovian effect, because past events or past choices have affected future outcomes. Now, in particular, what a process tensor is able to do is it's able to propagate this quantum state along and account for the control operations that manipulate that state. Every time you apply a different control operation, the environment is going to respond in a slightly different way, because the information that is transferred is going to differ. So every time you apply a control operation, you learn something different about this quantum stochastic process. And in particular, we can imagine that sequences of control operations are actually observables of the process. So what that statement means is that there exists some underlying process, and every time you apply a sequence of control operations, you are learning something about that process, right? You're obtaining some information which is like an observable of that process. So control operations in this context, you know, they can be things like unitaries, they can be things like noise maps, but in particular, or in maybe full generality, these can be quantum instruments. So a quantum instrument, if you're not familiar with it, is essentially, it's just a completely positive trace non-increasing map. So a dynamical map which can be non-deterministic. So for example, like a mid-circuit measurement and then a repreparation is an example of this. And you can imagine that if you apply multiple sequences of control operations, each with different outcomes, then you're going to get a joint probability distribution across time. You know, you're going to get a probability distribution which has your detector clicking with outcome xj at time tj, as well as xj minus 1 at time tj minus 1, all the way up to x0 at time t0. And this is all conditioned on the particular choice of instruments that you make. So in the same way that, say, a density matrix generalizes a classical probability distribution to the quantum setting, so too does a process tensor generalize a classical stochastic process to the quantum setting. So in the state case, you pick a basis in which to measure a many-body state, and you obtain some joint probability distribution conditioned on that basis. Here, we're just thinking in the temporal setting, we apply a sequence of control operations, and we obtain a probability distribution, a joint probability distribution conditioned on that sequence of control operations. Now, what's particularly nice about this is that it comes equipped with a generalization of the Choi-Jamiakovsky isomorphism to the multi-time setting. So the CJI, if you're not familiar, in the dynamics case, also known as the state channel duality, allows you to represent any quantum channel or any quantum map as a quantum state, a bipartite quantum state. And properties of that state tell you things about that channel. This can be realized in a similar way, or like the mathematical relationship is quite similar in the multi-time setting, which is that if you fed in 1/2 of a bell pair at each time and let it participate in the dynamics, and then rearranged these systems at the end, then the resulting many-body quantum state can be shown to be element by element identical to this multi-time process here. So what that means is that we can identify subsystems of this state with indices given here. So for example, we can identify this first subsystem, this O0, as being the subsystem associated with the average state of the system at time t0, for example. Now, what's useful about this is this allows us to map temporal correlations onto spatial correlations. So it allows us to understand temporal correlations using like our usual notion of quantum information toolkit. So what that means is that properties of the state are properties of the process, and a process is Markovian if and only if this resulting many-body state is a product state. So this is an important notion because the marginals of this process we can identify as being the CP-TP maps taking us from one time to the next. And if these marginals are correlated with one another, then we can, then firstly, that is a signature of non-Markovianity. But what this really means is that we can think of a process tensor as being a sequence of possibly correlated dynamical maps. And operations are observables on this many-body state. So is everybody happy with this so far? Don't know if...
Yes. You can continue.
Yeah. Okay, cool. Because I want to get into we have a few different works in reconstructing this process tensor. So given some experimental setting, I've stated that sequences of control operations are observables. And since this is a linear map on which we have observables, then we can reconstruct it using principles of quantum tomography. So in particular, every time, so we're now kind of dealing with this setting where we have a quantum computer, we want to characterize it to learn how it interacts with its environment. And so every time I apply a series of control operations, then through this generalization of Born rule, I determine something about my process tensor, which is depicted by this epsilon here. And so if I run enough different sequences, then that allows me to fully reconstruct the underlying map. And we can do this in a way which respects the physicality of the process. So if we want it to be positive, we want it to be, we want it to produce positive probabilities, and we want it to be causal in that future operations shouldn't affect past statistics, then we can come up with, we have algorithms to essentially find a maximum likelihood estimate, finding the maximum likelihood process tensor, which is as consistent with the data as possible. And so once you reconstruct this, you then have an object which tells you every possible piece of information that you can find out about that underlying quantum stochastic process. And importantly, this is in a purely operational setting. So this is independent of the underlying physics. So I haven't actually, so this isn't the point of the talk, but you know, if you want, I can show you some of these things at the end. But the point of this is that we can reconstruct these process tensors, and these process tensors can tell us about the underlying temporal correlations, so any underlying system environment memory. And this has applications to quantum devices, because it both gives you a diagnostic of the process and it gives you a prescription of how you can optimally control that device in order to mitigate these effects. Okay, so now I want to get into sort of the main point of the paper for which this talk is about, which is how can you distinguish between different environmental sources? So what I mean by that is, you know, if you imagine, you know, we're looking at this picture here, we've got an array of qubits, and our system qubit is interacting both with an inaccessible environment, but also with other controllable qubits, right? And this is an effect predominantly known as crosstalk. If I study the correlations, the temporal correlations of my system, then I don't actually know, you know, I only get a sense of exactly how correlated in time that system is, but I don't actually get a sense of where the correlations come from. So in particular, temporal correlations that come from a nearby defect compared to a nearby qubit, these are dynamically equivalent, but we maybe want to make the conceptual distinction that nearby qubits are controllable. And so there's sort of like a conceptual distinction between crosstalk in this sense and non-Markovianity, which comes from the bath. And so the purpose here is to say, well, how can we actually use our controllability of qubits in order to answer this question? So to do this, we use the classical shadows formalism. So this has obviously become very famous in the last few years, so I will kind of briefly go through it, but the sort of underlying premise behind classical shadows isn't so important to answering this question so much as the consequence. So in classical shadows, the general idea is that if you have a quantum many-body state, you can make lots of randomized measurements on that state, and the collection of data is able to tell you about many different observables at the same time. So the protocol works essentially as follows. So pick a random basis in which to measure your state, and then projectively measure it. So you transform your state rho with some unitary, you make a projective measurement, you get outcome B, which is some bit string. And so you know that the pre-measurement state is just the reverse of the unitary acting on whatever bit string that you had. On average, if you do this for lots of different measurement operators, then you can define a quantum channel, which is the expectation value across the ensemble of unitaries and of these measurement outcomes. And so a crucial kind of part of this is that this quantum channel can be inverted. And if this quantum channel is inverted and applied to your single measurement snapshot, then under expectation, this is exactly equal to the quantum state. So you can imagine that every time you make a single shot measurement and you get a pre-measurement state, that you're sampling some piece of information about the state. And so if you do this lots of times, you can do effectively like a Monte Carlo sampling of the state. And so collections of these snapshots define what is known as the classical shadow. So you can imagine that you pick lots of different bases in which to measure, you get lots of different outcomes, lots of different bit strings. And for each one of these outcomes, of which each one of these, we can effectively, we can take this data set, we can group it into different, we can, collect it into different sets of these states and average them together. And so the average is sort of like a representation of the quantum state. Now, the statement on classical shadow, that if I have m observables that I want to determine on my quantum state, then I can compute these m observables, or I can estimate these m observables by computing them across my data set here. And the statement is that log m 3 to the k over epsilon squared, order of that, local measurements are required to determine m observables with locality at most k. So what this means is that if I'm interested in observables that contain at most k traceless Pauli terms, then apart from this exponential overhead due to that weight, I can determine linearly many observables with only logarithmically many measurements. So this is kind of, yeah, I guess just a brief overview of classical shadows, but it's really this final statement which is the most important and the thing which is really pertinent to this this work, which is that you can use this, for example, to find all of the k body marginals of a quantum state in a way which grows only logarithmically with the number of qubits, say. So to bring this back to processes and non-Markovian processes, so we made the observation before that sequences of control operations are like observables on a quantum state. A process tensor can be represented as a quantum many-body state. And so indeed, we can apply the classical shadow formalism to learn properties of our process tensor across many different qubits and many different times. And the reason why we might like to do this is that the size of this object grows extremely quickly with the number of qubits and the number of time steps. So it's both exponentially large, both in the number of qubits and in the number of steps where we wish to characterize it. So what shadows allows us to do is it allows us to effectively have a compressed characterization technique, which tells us some pieces of information about the non-Markovianity, even if we don't get access to all of it. So,
hi, Greg.
Yep.
Could I just ask one question? Perhaps a naive question, but if you go back to the previous slide.
Yes.
On the definition that you say that is the important one, that you can use this local Clifford measurements to obtain this M observables. You also state the locality at most k. I think perhaps I missed. How do you define the locality here?
Yes, I actually realized I haven't written that. So if you have an observable on n qubits, the locality is the number of, If you have an observable on n qubits and you consider this to be the tensor product of different Paulis on those qubits, the weight is the number of non-trivial Paulis in that observable. So if you have like identity, 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 x, 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 identity, 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 that so basically the number of traceless Paulis which show up in your tensor product observable.
Okay.
So this
So it's the number of like operator is like not non-identity one. I just come with the number of like x or z, y.
Yeah, traceless.
Okay.
Yeah, exactly. So the consequence of this is that, like, say I have a 10 qubit state, and I'm able to determine all of the weight 2 observables. Then the consequence of that is that it allows me to determine all 2 body marginals of that 10 qubit state with only logarithmically many measurements in the number of qubits.
All right. Thank you.
Cool. So that's, you can do lots more with this, but that's kind of the pertinent part to
Sorry, I have a follow-up question.
Yep.
You are talking about the locality in space, but in your case, you are converting them to the time space. So your locality in your case, is it crossing different time? Is that right or not?
Yes, exactly. So we are associating a different Hilbert space with each time in the process tensor framework. And so we're identifying, like an input space and an output space of our process. And so, yeah, locality in this sense means observables which are acting on different times or different qubits.
I see. So I have another question. Since you are converting the channel into the according to the duality, transform them into a many-body correlated state. So, but I mean, when you do the measurement in different time,
Yep.
It will correspond to measurement in the state at different position or in different. I mean, do you because when we do the measurement in for quantum mechanics, the state will be changed. I mean, it will collapse to some state.
Yep.
So does it matter to your case to further analyze?
No, so that is a good question. So one of the key principles of process tensors and what we're dealing with here is that we have a different Hilbert space or a different subsystem associated with the output and the input to the process. So you can imagine that you make a measurement of the system, you might collapse the state, but then you freshly re-prepare it in a different basis and then insert that back into the process.
Okay, so you definitely will change the state after the collapse, but you refresh it to do further step, and you want to analyze the original state. Is that correct?
Yeah, so you want to analyze how the dynamics responds to the operation that you applied to the state.
Okay.
And the only way that you can do that is if you know that you collapse the state and then you re-prepare it, you know exactly how your control operation affects the state.
I see. Okay, thank you.
Cool, no worries. So each of these measurements, I should emphasize, each of these measurements and each of these preparations corresponds like a measurement on the choice state of the process tensor. So this is a quantum many-body state, and we can imagine that different operations at different times allow you to learn something about the state. So what that means is, in the context of classical shadows, we should be able to apply the exact same principles to determine low weight observables of a process, both in space and time. So this circuit this circuit effectively indicates the protocol for how you go about doing this, which is we have a whole bunch of different qubits. At each time, we make a measurement on every qubit in a different random basis, and we record the outcome. We then freshly prepare the state of the system in a completely different random basis. And you do this for all qubits at all different times. So each run of the circuit, each shot, gives you a snapshot of the process tensor as it's defined over time and space. And so what we're learning is we're able to determine information about so these input legs and these output legs at different times. So we can associate this with marginals of this process tensor being the dynamics of each qubit between each time. And then we can look for correlations between these things. So as an example, in this works here, referenced down the bottom, we looked at using classical shadows for detecting correlated noise on IBM quantum devices at different times. So here we had a 7-step process, and we wanted to know how correlated each step was with each other step. So if we treat them as dynamical maps, say from 1 to 0 with 3 to 2, and we can compute the total level of correlation which exists between these. So this left heat map, the bottom half of this gives us the total non-Markovianity, so the total correlation between these different types, and the top half of it indicates the entanglement which persists between different times. We can also look at things like the probability of correlated Pauli errors occurring on the system. So like, what's the probability of getting a Z error at time 0 with a Z error also at time 5, for example, and then determine these. So this sort of information gives you detailed diagnostics of the type of noise which might be present on your device. But this is just like a background application which we've used in a different context. So I want to return to how to interpret the types of observables which classical shadows gives you access to in the spatiotemporal setting. So in particular, so as I've kind of emphasized.
Sorry, can I ask a question? Hello? Sorry.
My
Wi-Fi died again. Okay.
I can hear you.
Okay. So here the noise is, the noise is not like I feel the noise is like just the not just like sorry, it like its environment, like it's there, because this way I feel it's not like, okay, I do some gate operation, then maybe there's a noise because my gate operation is noisy. So it's kind of, the noise is attached to the gate. But here it seems like, okay, it's just the space. Then there's just noise there, and it's not like we are analysis the gate noise.
Yeah, that's a very good point. So I'll make 2 comments. So yeah, I haven't mentioned this, but yeah, you're absolutely right. The gates themselves can be noisy, and so we might not know exactly what gate we're applying. Say if there's some coherent error or something like that. For the sake of this, I will say that we're treating the gates as perfect, but we do have methods for dealing with this, which is that we can make the method self-consistent by estimating both the gate and the process at the same time. And so that doesn't assume anything about the gate itself.
Okay, so it's kind of like the gate noise is also including the process tensor.
So it's not explicitly included in the process tensor, but you can model it simultaneously. Yeah.
Okay.
But that is a very good point.
Okay, thank you.
Cool. So just re-emphasizing that what classical shadows gives you access to are low-weight observables. So you have a number of traceless Paulis on some of the subsystems with identity on the remainder. And we want to be able to interpret what these observables mean in this Choi picture, so in this temporal picture. Now, what actually happens is that it turns out that the identity operation, so the identity acting on some output followed by some input, you can think of this as being equivalent to tracing over the output of a system, so tracing over a system and then preparing a maximally mixed state. So equivalently, you can think of this as picking an operation whose Choi state is represented by the identity, and this operation is the maximal depolarizing channel. So the maximal depolarizing channel in this context is the channel in which you maximally, you measure the system, you throw away the outcome, and then you insert a maximally mixed state for the dynamics. What's interesting about this is that the depolarizing channel is actually a causal break. So what I mean by a causal break, let's consider these two pictures here. Say you apply some generic A0, then information can persist. So we apply some A0 at time t0 and we apply some A1 at time t1. Information from the past can persist to the next time, either through the system or it can go into the environment and then, as mediated by this interaction, come back to the system. There's no way to tell the difference between these two cases unless you have a causal break. So a causal break means that no information persists through the system. And so if you detect correlations between time 0 and time 1, then you know that information had to have gone through a different quantum system as mediated by the interactions. So what this allows you to do is it allows you to effectively perform a kind of causal testing. You say, I know I have correlations, and I'm going to eliminate one of my systems. And so if I have correlations still with that one system eliminated, I know it had to have come from a different system. And this is this gets to the kind of the crux of how you distinguish between correlations which might be due to the collapse of a quantum system due to your measurement, and correlations which are due to information from the external environment. Now, why is this interesting? Well, it's interesting because if you imagine that you have a system and it has temporal correlations, you've detected it's non-Markovian. Now you want to know, did this information come from an external environment or did it come from local qubits? So you can imagine that at each time, information is passing from the system to its neighboring qubits as well as an environment. And so you could distinguish between these different sources if you can control them, because say in this instance, I have control over qubit 3, I can apply a causal break to the system, and that will stop any past future information from propagating. The information which comes back into the system does not depend at all on the past. And so if I still detect correlations, then it can't be due to that system. So this picture here, what this indicates is this is a depiction of a process tensor, and we can split up the memory into different subsystems. So we can split it up into the environment and the nearby neighboring qubits. What classical shadows allows us to do is it allows us to perform these depolarizing channels non-extensively. So we essentially get them for free, regardless of how many qubits we're looking at, but we get them with only logarithmic overhead. So the point of this is to say that we could characterize temporally the temporal correlations on a system with the remaining qubits kind of erased. And if we detect any temporal correlations, then we know that had to come from the external environment. And since we can do this for all qubits at the same time, we can efficiently characterize an entire grid of qubits to see the environment memory. So we could look at different marginals of the process tensor. We could either look at different dynamical maps on different qubits at the same time, and this would allow us to identify spatial correlations. If we looked at a single qubit at one time and a different time, that would give us temporal correlations. And if we looked at a single qubit at one time with a different qubit at a different time, then this is spatiotemporal correlations. So correlations which persist between space and time. So here are some, this is kind of showcasing this idea in action, purely numerically. So imagine we have a grid of qubits, and I'm going to say that each qubit interacts with its neighbors via a ZZ interaction. So this is quite common, for example, in trans-1 qubits. And there's a defect in the environment with which the qubits also interact. Now, if I performed process tensor tomography, so if I performed, if I characterized the temporal correlations on any qubit from, over a couple of time steps, then I would see that they're all non-Markovian, because each neighboring qubit is coherent and we've got crosstalk between the different qubits. But if I use this method of effectively shadow filtering, where on each qubit I characterize its correlations with the other qubits erased, then what I can see in this second picture is that it's only the qubits which are near this defect which show temporal correlations, which in essence is a statement that only these qubits are near an inaccessible bath environment. So this might be the type of non-Markovianity which exactly I'm interested in, because it filters out the effects of the local qubits, and it does so without costing me any extra resources in my characterization. What it allows me to also do is, if I look at spatiotemporal correlations, then it allows me to identify shared baths. So suppose you have two qubits which are commonly coupled to the same environment. Then information could travel from qubit 1 to the environment at some time, and then at a later time come back into qubit 2. Then these two qubits will be correlated in both space and time, because a past action on a single qubit could impact the future dynamics of a different qubit. And this would be an indication that they're coupled to the same bath. They have a common cause variable. So what this numeric shows, if we want to explore this idea, so in figure panel A of this, we have a similar thing to previous, which is that we have a grid of qubits, except now we have two defects, say. And we also have, so we have the nearby qubits are coupled to the defect, and then every other qubit is coupled to its neighbor via crosstalk. So we could determine the non-Markovianity of these again, using just regular process tensor tomography. And that would tell us that everything has temporal correlations. We could then do this shadow filtering to determine which correlations are responsible, which correlations have the inaccessible environment as their progenitor. And we would find that it's the ones which show non-zero numbers. So top right, this red one here, this purple one, and so on. But what we can also... Yeah.
Quick question. So in this square figure, what's the horizontal and vertical direction? I mean, one is qubit direction and the other is time direction. Is that right? Or you are talking about the two-dimensional qubit? So
yeah. So this is a two-dimensional array.
Okay.
But both dimensions are spatial dimensions. So it's really just a lattice of qubits.
So you are not discussing in the randomized way, randomized benchmarking way in the circuit. You are not talking about that.
So yeah, this isn't a randomized benchmarking type approach. So this is saying we measure the process tensor. So we measure, say, 2 different or 3 different steps on each qubit, and then we determine its temporal correlations. And then this is a heat map of the different temporal correlations. But this is all numerics.
Oh, okay, I see. Okay, thank you.
Cool, no worries. So in this first panel, we're looking at purely temporal correlations, and we can see which spatiotemporal correlations, so the marginals on one qubit from one time to the next, and a different qubit from a different time to the next. And the correlations between these can only be as a result of a shared bath. And so what this allows us to do is, when we compute these correlations, this is measured as the quantum mutual information, but the exact number is not important. These correlations allow us to say which qubits have a common cause environment. So we could see that, the qubit that I'm highlighting here has a common cause with this qubit, and this qubit. but it does not have a common cause with this qubit, because even though the latter case is non-Markovian and is coupled to a defect, it's actually coupled to a different defect. Cool. So I guess I hope I conveyed this clearly, but this is the basic premise, which is that so we can use these techniques of process tensor tomography to determine temporal correlations, but they don't allow us to distinguish between origins of those temporal correlations, so different parts of the environment. And so what the introduction of classical shadows allows us to do is it allows us to perform causal breaks and determine the process tensor on each qubit with a causal break applied to each other qubit. And this hence filters out the non-Markovian effects due to passive crosstalk with those other qubits and allows you to see what is the noise due to an inaccessible environment. And I will just state, so the filtering that's done here it's not unique to process tensor tomography. So this observation could be, for example, similarly applied to some people in your group have worked on non-Markovian randomized benchmarking. And so if you determine temporal correlations with these sorts of techniques, with the remainder of the qubits filtered out effectively, then the conclusions are the same. So yeah, so thanks for listening. Thanks for having me. Let me know if you have any questions.
Thank you very much, Greg, for the very nice presentation.
Thank you.
So as he said, does the audience have any more questions for him?
So in your numerical simulation, how do you define the environment? So is all the qubit far away you define as the environment, or where is the environment exactly?
So the environment is anything which is uncontrollable. So here, for example, we're considering a scenario where maybe each qubit here is something that we've fabricated, so something which we can apply gates to. But then the environment is some two-level system which we don't have control of, but nevertheless is coupling to our different qubits. And so the distinction between environment versus system here is that the environment is everything which is not controllable by the experimenter.
So because I'm thinking about the circuit, so when you are doing circuit and simulation, there are the system part and the environment part. So there are other qubits prepared for as the environment. But in your case, how do you model the two-dimensional array? You just model it and with some noise model, or you add auxiliary qubit as the environment. So or you are doing the real device simulation and
so this particular demonstration is just if I understand your question correctly, this particular demonstration is just like a numerical analysis where we have a bunch of qubits. So we have here 15 qubits, and we have one defect sitting in the environment. And I'm applying a Hamiltonian, which is a ZZ interaction between nearest neighbors. So maybe I could have sketched that out better, but a ZZ interaction between nearest neighbors. And then the 4 qubits which are closest to the defect have an exchange interaction with that defect, so like a Heisenberg interaction. And so the simulation is just like a solution of that Schrodinger equation, but with different operations applied to different qubits.
So you basically apply a Hamiltonian to the system. And so the 16 qubits are all the system, or you just define the subregion as the system? That's my question.
Oh, I see. Yeah. So the 15 qubits, these are all the system.
Oh, okay. So your Hamiltonian has some damping effect, or you already include some noise model in the Hamiltonian? Otherwise, how can you see the environment?
Yeah. So the Hamiltonian includes interactions with the environment. So this is like a fully dilated simulation.
Okay, fully dynamic. Okay, I see.
Yeah, but you could definitely do that. But I guess the key thing is that this method of looking at dynamics assumes nothing about the interactions. It's really just, apply operations to different qubits and then measure their state at the very end.
But do you only do the measurement at the very end because you want to filter out some qubit and see, or to perform some causal break according to your terminology?
Yeah, sorry.
So after the causal break, you feel how do you do the filter? You just cut the interaction of this qubit to all other stuff, or how do you do the causal effect and then to perform any measurement during the causal break?
Yeah, sorry that I misspoke. So you do measurements in the middle of the circuit. So oops, so this is like a circuit depiction of the procedure where on each qubit you do measurements at different times and you freshly prepare the system at different times.
So so the Hamiltonian are all the same at all times, except during the measurement you refresh the state, and all other Hamiltonian evolution are the same, right?
Yes. Yeah.
I see. Okay, cool. Okay, thank you.
Cool. All right.
All right. Do we have more questions?
Okay. Could you make it like addressing a little bit more about the how do you specify the non-Markovian? Like whether the two qubits they have the same like they are affected by the same path, or
Yep.
they only affect on the they affected by the different one.
Yep.
Like I know like the cross, you can filter in the crosstalk, but I think I kind of lost there. Like how do you specify them?
Oh, so that's not. So this is a product of the simulation. So I've set up a simulation where each defect interacts only with the qubits which are geometrically closest to it.
Okay.
So this defect here, this 0,3, for example, is only interacting with 0,2 and 1,3, whereas this defect here is interacting with the 4 qubits that are around it. So the point, I guess, is that once you do the filter and you look at the spatiotemporal correlations, you can determine which qubits are spatiotemporally correlated with other qubits, and if they're not correlated with one another, then that tells you they don't share a common path.
Okay. So this like here okay, so here you can I mean, so this is because we have this simulation, so
Yep.
we just filtering out the crosstalk, then we have this result. So it's not like, okay, if it's an unknown case, then I can specify whether it's it has the common path or they are separate.
Yeah, that's exactly right.
That's maybe another direction of research.
So yeah, so this is a characterization technique. So
Okay.
so if you were to apply this in practice, you would have a grid of qubits on your device, and you would that they don't share a common path, and that would tell you something about the device.
Sorry, wait, the internet is not condition is not well. Could you repeat a little bit?
Sorry, yeah. So just stating that this is intended to be a characterization technique for, for quantum devices. So if you perform this in practice, then you would get a grid of information about which qubits were correlated with which other qubits. And in particular, you could determine which qubits had shared baths and which qubits didn't have shared baths. So you could come up with different kind of causal regions. But this would all be depending on the exact device physics.
Okay, thanks.
No worries.
Sorry, can I ask a further question?
Yeah, of course.
Yeah, and when you do the causal break, you do the measurement and perform prepare a fresh state to continue. And usually, how many measurement is needed? Do you try to reduce the measurement time according to the shadow tomography, or you how do you quantify the number of measurement times? Is it
yeah. So So if you were to characterize, if you were to fully determine a process tensor on a d-dimensional system for k time steps, then the number of measurements grows like d to the 4 times k, or d to the 2 times k, sorry. Here we fix the number of marginals that we're interested in. So let's say we're interested in 2 body marginals or 3 body marginals or so on. Then the number of measurements is first fixed by effectively 3 to the power of k, where k is the number of bodies we're interested in, or if we're talking about times, then it's double that. But it's exponential in the locality, so the number of terms that you're interested in. But once you fix that, it only grows logarithmically in the size of this. So it only grows logarithmically in the number of steps and the number of qubits. And so that means that applying the causal break to any extra qubits at any extra times, the resources required for that only grow logarithmically. So not too expensive.
Okay, I see. So basically, you use this classical shadow concept to do the causal break preparation, but I mean, classical shadow can also estimate some expectation of observables. So that part you didn't use it, or it can be further used in your case.
So the estimation of observables is what allows you to estimate the marginals of the process. So you use some pieces of information to estimate the marginals of the process. But the nice thing about classical shadows is that you get these other identity terms for free. And so they act as a causal break on the remainder of the qubits. So what this means is that you can simultaneously estimate all, say, 2 or 3 or 4 body marginals of this process with everything else erased or filtered out.
So you mean your observable, especially the leftover process tensor?
Yeah, the observable is the process, like is an operation on the process tensor. Exactly.
I see. Okay, thank you. That's very cool idea. Okay, thank you.
Thank you.
Okay. Yeah, indeed, it's very cool. So do we have further questions? All right, perhaps not the case. So I wanted to thank you again. Thank you very much for coming here, giving us very nice talks about a very cool subject.
No worries. Thank you very much. Thanks for thanks for having me, and also, yeah, very nice to meet you all.
Okay. Thank you. See you.
See ya.
Okay, thank you
Okay,
very
we'll
much.
see you soon.
Yeah, feel free to yeah, we should email a little bit about some of these.
Yes.
things.
Yes.
Yeah, sounds good.
Let's get in touch about this. Whether we could collaborate.
Sounds great.
Okay, great. Thank you so much.
Okay. Thank you. See ya.
Thank you.
Thank
Bye-bye.
you.
Bye bye.